So this chapter is pretty intense. It's technically it's a unit, but I'm going to split it into two parts, but it's still all acid and base material. 1000% there will be acid-base questions on the AP test, like without a doubt. So this is a really, really important chapter. It's a pretty intense chapter, so I highly recommend do not fall behind at this point. This would be a really, really difficult time to start getting behind in here, okay? So we have to do a little bit of a flashback because it's been a while. It's basically been since our aqueous solutions chapter, which was chapter 4, where we've learned about, I'm not screen sharing, sorry, where we talked about who our strong acids and strong bases are. So we need to kind of refresh. We need to refresh who they are. So here we go. Your 6 strong acids are HCl, HBr, HI, H2SO4, HNO3, HClO4. So basically from here on out, you need to know these. If you are an acid and you are not one of these 6, you're weak by default. So if you're not one of these 6 and you're an acid, you are a weak acid. So instead of memorizing all acids ever, as long as you know your 6 strong acids, any other acid is weak. Okay? So now let's refresh our memories on who our bases are. So does anybody remember what bases have in them, or what we told you a while back? Hydroxide, okay? So all of your alkali metals, that's your first family, right, with hydroxide. So we've got who? Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. And then now francium is radioactive, so we're going to kind of ignore it. And then 3 of your alkaline earth metals with hydroxide are also strong. CBS, calcium, barium, strontium. Now your alkaline earth metals have a +2 charge, which is, and OH has a -1 charge, which is why you have to write it like this. Calcium, barium, strontium. Okay. Now, if you're a base and you're not one of these, you're a weak base. So as long as you know you're strong, guys, everybody else is weak. Okay. So this next slide kind of shows us we have our normal strong acids and our normal strong bases. And then like a lot of our organic acids, those are acids with like carbons in them, are weak acids. So like acetic acid. Another big one is HF. A lot of kids think HF is strong and it is not. So be very, very careful with HF. And then like weak bases are things like ammonia. There's also a lot of organic bases. Look at this. This guy's name is called methylamine. And this NH2 group is what makes it basic. But it's organic because it has a bunch of carbons and hydrogens also with it. So that's an organic base. But again, as long as you know your strong acids and your strong bases, if you're not one of them, you're weak by default. Okay? H2SO4 is one of the strong, yes. Ooh. So just some general properties. Acids tend to have a sour taste. So think of like acetic acid is in vinegar. And then we have things like citric acid in our fruits, like oranges and lemons and things like that, that kind of sour taste. Whereas bases tend to be like bitter, like broccoli is a pretty basic fruit. Baking soda is basic, soap is basic, and bases also have kind of a slippery feeling to them. Your blood is also slightly basic, and it's also considered what's called buffered, meaning it resists big changes in pH because your blood needs to be a really, really, really specific pH, or it could be harmful to you. And we'll talk about buffers in the second part of this chapter. Okay, so these are just general properties that you probably learned at some point already. Okay, so there are 3 different ways to describe acids and bases. There's like 3 different acid-base definitions. The first one we're going to do is a Lewis acid base, how you identify an acid and a base based on this definition. And I'm going to show it to you, and then we're never going to talk about it again. It is not on the AP test. Okay? The Arrhenius acid and base is the way you actually already learned. We had to kind of cheat and teach you this way when you learned how to name. Otherwise, you couldn't do naming. So this is the way you actually kind of know already. And then what we're going to do mostly today is the Bronsted-Lowry acid and base definition. Okay, so the 2 and 3 are big. Number 1, I'm going to show you, introduce it, and then we're not going to worry about it after that. Okay, at least not for this class. So by definition, a Lewis acid is an electron pair, so 2 electrons, acceptor, it takes them in, and the Lewis base is an electron pair donor, so it gives them away. And they usually do this in order to form a chemical bond. So let's draw these 2 structures. If you remember how to do Lewis structures, let's draw BF3 and NH3. So BF3 is trigonal planar, whereas NH3 is trigonal pyramidal because it has that lone pair on the nitrogen. Now, if you'll remember, this structure with boron in it has an incomplete octet. There are only 6 electrons around it right now, and it's actually okay. It's stable that way. The thing is just because it has 6 electrons around it doesn't mean it can't hold up to 8. It absolutely can. It has the ability to have 8 electrons around it. It's just okay sometimes if it doesn't. So what happens here is this lone pair of electrons on the ammonia basically get given to the boron, and they form a bond. They make a chemical bond. So this guy didn't have any. This guy had a pair of electrons. And then you end up making this funky looking thing, where you have the boron attached to the 3 fluorines. And then these 2 electrons are now a chemical bond. And then you have the NH3. Okay. So this accepted the electrons, and this guy donated it. So when the boron accepted the electron, this is your Lewis acid. Whereas the ammonia donated its lone pair of electrons, so that would be by definition what a Lewis base is. Okay, again, this is no longer a part of the curriculum, so I just wanted to introduce it to you, and then we're not ever going to talk about it again for the sake of this class. Okay, so the Arrhenius acid and base definition is one you're more familiar with. Basically, we told you anything that had a hydrogen ion or a hydrogen out in front, we identified as an acid. So the ability of something to produce hydrogen ions makes it acidic. The presence of H+ ions makes something acidic. And the presence of OH- makes something basic. This is kind of like the cheating definition we told you when we first started naming acids and bases. So if you have an H+, you're an acid, and if you have an OH-, you're a base. And this is a decent general definition of acids and bases. But the problem is, and especially for bases, that this doesn't encompass all acids and bases. So while this definition isn't awful, it's just not complete. Because there are plenty of bases, for example, that don't have hydroxide in them, and they're still bases. So while this does a decent job of describing an acid and a base, it doesn't do as complete of a job as what we're going to show you. Okay, so like HCl, it's an acid. Why? Because it has an H+ ion. NaOH, it's a base. Why? Because it has a hydroxide ion in it. That's the Arrhenius acid and base definition. If you have H pluses, you're an acid. If you have OH minuses, you're a base. And again, this isn't wrong, it's just not complete. So, for example, NH3, ammonia, is a base. It's a weak base. I don't see hydroxide in there, but yet it's a base. So that's like the limitation of the Arrhenius definition. Like, yes, hydroxides are base, but they're not the only bases. Not every single thing has hydroxide in it. Sodium bicarbonate, baking soda, is a base. I don't see hydroxide in there. So there's limitations on the Arrhenius definition, especially for our bases, okay? For the sake of this class, things that you see with an H plus ion or a hydrogen ion are going to be acids. But not all bases show up with hydroxide ions. Some of them do, but not all of them. Okay. So the definition we're going to work heavily with today is the third one. It's called the Bronsted-Lowry definition. And this one is a little bit more complete, but this one shows you basically the transfer of hydrogen ions, which they sometimes refer to as proton transfer. So in this chapter, if you see proton transfer, they're talking about H plus ions, okay? So the Bronsted-Lowry definition is really going to make a lot more sense when we do a practice problem. So I'm going to kind of explain this, and then it will make tons more sense when we practice, okay? So by definition, a Bronsted-Lowry acid loses a hydrogen ion, or donates it. And then by definition, a Bronsted-Lowry base accepts the hydrogen. So the acid gives it away while the base takes it in. So one thing's losing a hydrogen and the one thing's gaining a hydrogen ion, okay? Now, when the acid loses the hydrogen ion, it forms what is known as a conjugate base. And when the base gains the hydrogen ion, it forms what is known as the conjugate acid. And then in a reaction, we will be able to identify conjugate acid-base pairs, okay? And again, this is going to make more sense when we start practicing with actual reactions, all right? Something that is going to be different in this chapter is you guys are used to recognizing this guy as acidic, which is fine, but I need you to also start recognizing H3O plus as also meaning acidic. This is just H plus in the presence of water, okay? That's how we get H3O plus. So they both mean acidic, okay? And the reason we say the presence of water is because most of these acid and base solutions are aqueous, and aqueous means there is water present. That's what it means to be aqueous. So again, we're going to use these like ions kind of interchangeably. They do mean acidic, both of them, the same thing. Okay, so what I want to do is, I feel like this slide can be confusing until we start practicing. I want to give you a reaction and I want to practice on identifying the conjugate acid-base pairs based on this new definition that we're looking at, this Bronsted-Lowry definition. So here is a general one, and you will see this a lot, especially like on the AP test as well. When you see HA, they just mean some sort of acid. What does the A mean? The A means like the anion part of the acid, right? So like HCl, HBr, HI, HF, HNO3, HClO4, whatever. It's H something, which makes it an acid, okay? Now, by definition, a Bronsted-Lowry acid loses a hydrogen ion. Well, let's refresh. Hydrogens are +1. Is that right? So if I lose a +1, the A becomes -1 because I just got rid of a positive charge. So this is the acid and this is its conjugate base. Now, the new definition we have is the Bronsted-Lowry definition of a base, where a base takes in or accepts a hydrogen ion. See, look at, they called that proton here. It means H+, okay? Well, if a base is neutral right here and it takes in a hydrogen ion, it becomes BH+, because the hydrogen is +1. So a base and its partner is called a conjugate acid. So two big questions I've gotten in this chapter are, will the acid always be paired with the base? Yes. They're called acid-base pairs. You're not going to have acid-acid or base-base. That would not work, okay? So an acid will always be with a base, and a base will always be with an acid. And then the next question I've been getting are the conjugates always going to be like on the right side and then like the regulars on the left side? Yes. That's just like a generic rule of thumb, that you start off with the acid or the base over here, and the conjugates will appear on the product side, okay? Technically, if you're at equilibrium, it doesn't matter which way you look at it, but you're gonna see the style to have your acid base over here and your conjugate acid base as products, all right? So let's try with like real chemicals, because these are like just generic, right? Let's try with real chemicals. So I have HClO2 and water in equilibrium with H3O plus and ClO2 minus. Now, before you identify like who's who, you should just pair up the things that look similar, like meaning the things that have similar parts to it. So like HClO2 looks very similar to ClO2 minus. They have similar things involved. And then H2O and H3O plus look similar. Now, this one's going to be kind of simple, mostly because when you look at this guy, HClO2, you probably know that it's a what? Acid, right? Because there's a hydrogen out front. So now, let's follow, though, the definition of what it means to be an acid. An acid will lose or donate the hydrogen ion. So look what happened to it. It no longer has the hydrogen ion because it donated it. So yes, that's the acid. So its partner is called your conjugate. Oops, I'll write it out first. Conjugate base. Now, if you already know one pair, by default, the other pair has to be the other. So if this is the acid reactant, the other guy has to be the base. Like, you don't really have a choice. So the water is acting like a base, which means its partner is its conjugate acid. So we have just assigned conjugate acid-base pairs. Acid-base on the left, conjugates on the right. And an acid is always with a base, and a base is always with an acid. So this brings up the point. Someone goes, well, if water can be a base, can it also act like an acid? And that answer is yes. We'll get to it in a second, but let's talk about why. Does anybody remember the other way to write water instead of H2O? HOH, okay? So let's look at this just real quick. This is H plus, right? H plus means what? Acid. What's this? OH minus. OH minus means what? Base, right? So that's what makes water neutral. H plus OH minus is neutral now to make water, but it has both acidic and basic properties, so it can act like both. There's a name for that. It's called amphoteric, and we'll get to that in a little bit. Okay? All right. So I'm going to do the first one with you, and then I'd like you to try to identify the pairs on your own. Now, again, some of these are obvious. Like HCl is hydrochloric acid, so it's an acid. But let's talk about how it follows the rule of acids. It lost or donated a hydrogen ion, okay? So conjugate base. The chloride ion is its conjugate base. So if the HCl is the acid, the water is the base, and the H3O plus is its conjugate acid. It accepted or gained or added a hydrogen ion. There are other chemicals besides water that are amphoteric and act both like acids and base, and we'll We won't get to all of them, but I'll give you another example in a little bit. So I just identified my conjugate acid-base pairs. So I'd like you to try to do the other two, please. So here are the correct answers. So NH4 plus is a conjugate acid, yes. NH3, ammonia, is a base. It's a weak base. Any questions before we keep going? Okay. So as I was saying, mentioned briefly earlier, an amphoteric, sometimes referred to as amphiprotic substance, is a substance that can behave both like an acid or a base, depending on who it's partnered up with. So later on in this lecture, we're going to discuss about identifying the relative strengths of acids or bases. So whether something acts like an acid or a base depends on how strong of an acid or a base it is. And we're going to determine strength by looking at K values, equilibrium values. So we will get into that. But we're going to first do a practice where I take this ion, hydrogen sulfite ion, and I'm going to make it in the first part act like an acid with water. And then in the second part, I'm going to make it act like a base with water. So the first thing I'm going to do is just write HSO3 minus. And they're asking you to put it with water, so I'm going to put plus water. Now, you might not know this yet, but this guy's weak, so I'm going to draw it with an equilibrium arrow. And now in this first one, I would like it to act like an acid. So now you're going to have to get good at actually showing how the products are made and who they turn into, as opposed to having them just be sitting there for you. So what does an acid do? By this definition, this Bronsted-Lowry definition, the acid is going to lose the hydrogen, right? So like this guy is not going to have a hydrogen on it anymore. So I'm going to end up with SO3, but SO3 2 minus, great, right? Because we got rid of a +1 charge. So now you're -2 instead of -1, right? H's are +1. Okay. Well, if this was the acid, that means water had to be the base, right? So basically this guy lost the hydrogen because this guy took it. So now if this guy gains the hydrogen, you become hydronium, which is H3O plus. There's now 3 hydrogens and a +1 charge. So this is a hydrogen sulfide acting like an acid. Well, now if I wanted to act like a base, let's look at how that goes. HSO3 minus plus water in equilibrium, and now this is going to be a base. So if this guy's going to be a base, it's going to take in or add or accept a hydrogen ion. So what does this become? H2SO3. There's an extra hydrogen, and then the +1 cancels out this -1, which meant the water had to act like an acid. So what do acids do? Well, they lose the hydrogen ion, or they donate it, right? Because this guy's taking it. There's like an exchange of the hydrogen ion. So I'm going to rewrite water so you can kind of see it a little bit better. What happens when water loses the hydrogen? Who do you have left? Hydroxide. So you should notice that while this guy is acting like an acid, it's producing acidic hydronium. And while this guy is acting like a base, it's producing basic hydroxide. Okay? Okay, there are other substances that are also amphiprotic. You don't need to know them or amphoteric. I just am showing you how they can behave both ways. Okay, this is kind of a review. The only difference between these two equations is the presence of water. But these two equations really truly do mean the same thing. This is some strong acid. I'm going to pick HCl. It is a very common strong acid we're used to, right? HCl in the presence of water makes the hydronium ion and Cl minus. Now, this right here is just a simplified version without water, where we're producing hydrogen ion now instead of the hydronium ion and Cl minus. These two equations mean the same exact thing. This is like the more elaborate way to discuss it, and the bottom one is just a more simplified way. Because remember, it is the presence of the H plus ion, or now we know the hydronium ion, that makes something acidic. But again, these two equations are basically talking about the same thing. One just has water in it and the other one does not. So you make the hydronium ion on one and just the H plus ion in the other. Now notice the arrow is one way. Why? Because strong acids 100% ionize in solution. So down here, I've done the same thing, but I'm discussing a weak acid. So my weak acid down here, I'm going to have it be HF. HF is weak. And then again, with water, you make the hydronium ion and F minus. And then just without the water, you make H plus instead and F minus. So H plus instead of hydronium. Again, these equations will be used interchangeably. The first one with the water is like more elaborate. The second one is just more of a shortened way to discuss the dissociation of the weak acid. And again, notice you'll see the equilibrium arrow as opposed to the one-way arrow for substances that are weak. Okay? So this concept is what is going to allow us to identify, well, part of it, of who is going to identify who's strong and who's weak. And so all this is saying is that if you have like a really, really strong acid, its conjugate is fairly weak. Whereas if you have a really, really weak acid, its conjugate is fairly strong. Okay? And because of that, we know which way the equilibrium or reaction lies. Let me see what my next slide is. Okay? So I'm going to show it to you this way. So let's talk about HCl, which is a strong acid. One-way arrow. So this is a strong acid. And then I'm going to talk about a weak acid, like HF. Now, weak acids, I'm going to do an equilibrium arrow because they don't 100% ionize. Okay, so here's the point. This is the strong acid, and this guy is its conjugate. This acid is so strong, and it produces such a weak, so acid, conjugate, base. This guy is so strong, and its conjugate base is so weak that, remember when you're a base, you're going to accept a hydrogen ion. So if this is a really, really crappy base, it doesn't do a good job of taking in a hydrogen ion. So like, it doesn't have the ability to get this back because it sucks as a base. Okay? Which is why we say the equilibrium lies, I mean, it like straight up doesn't even go to equilibrium. This is all the way to the right. Okay? This guy completely ionizes, and neither of these are strong enough to try to go backwards. Okay? Now, the opposite is true for weak substances. So this is a weak base. So a weak acid, excuse me. This is its conjugate base. Okay? Weak acids, or weak whatever, it doesn't have to be an acid, it could be a base. Weak substances have pretty strong conjugates, meaning this conjugate base is relatively strong. So what do we know that bases do? Bases accept hydrogen ions. So when this guy dissociates into this guy, and this guy's like, ooh, I'm pretty strong, I'm going to yank a hydrogen back. It just goes like, whoop, and makes this guy back. So like it tries to ionize, but the fluoride is such a strong base that it just repulls the hydrogen back to itself to form this back, which is why the equilibrium for weak substances generally lies pretty far to the left. Most of the substance is the HF and not the ions, which is the exact opposite of what strong substances do. The strong substances produce such weak conjugates that it can't go backwards, which is why we do a one-way arrow. Whereas the weak substance produces a strong conjugate and it like tries to ionize and the fluoride's like, nope, and it yanks a hydrogen back to reform this guy. Okay? So the question becomes, well, how do we know how strong or weak they are? Well, we're going to use charts for that. There's no way you can just look at one and know, with the exception of knowing that weak have strong conjugates and strong have weak conjugates. Okay? So let's go back. Okay? Let's talk about 3 or 4, different diagrams where we're trying to identify who is strong, who is weak, and concentration. So you'll notice that the intact thing is your substance not ionized. So this is some sort of acid, H whatever. So H is your green, and then the pink is your conjugate, whoever it is, F minus, Cl minus, Br minus, NO3 minus, whatever. So you have 4 beakers. And the first question asks to pick a diagram that's fairly concentrated, but a weak acid. Now, notice these little white spheres are your water molecules. So if you want something to be concentrated, you don't want a lot of water molecules in there. The less water it is, the more concentrated it is, right? It's like if you make Kool-Aid with the powder, the less water you put in there, the sweeter it is, the more concentrated it is. So we also want it to show mostly weak acid, meaning you want to have a diagram where the molecules are not ionizing significantly. They're only ionizing a little bit. So which beaker do you think is the best representation of a weak acid with fairly high concentration? Good job, Andrew. It should be B. Look at the acid mostly intact here, and also does not have as many water molecules as, let's say, this one. There are a lot of acid intact here, but there's a lot more water molecules. So while it's definitely a weak acid here, this is a lower concentration. So B. So which diagram is concentrated again, but more represents a strong acid? Well, remember, strong acids should ionize more completely. So you should see less of the molecules stuck together and more of them spread apart from each other. And then again, high concentration should have less water molecules. So that's definitely looking like C. They're more split apart, okay? Look at how they're together as opposed to here. They're not as close together. They're more ionized. And then there's less water molecules in it, so that would make it more concentrated. So now we're going to assign the relative strengths and concentrations to the 2 remaining diagrams. So this guy should be a weak acid. I see most of the molecules intact. They're not ionized significantly. But there's a lot more water molecules, so this would be like a lower concentration. Whereas this has significant ionization, so more like a strong acid, but there are a lot more water molecules, so lower concentration, so more dilute. Okay? Okay, so again, the stronger the acid, the weaker its conjugate, and vice versa. So for example, this is a weak acid, which means its conjugate is strong. This is a strong acid, which means its conjugate is weak. So if the conjugate is strong, the equilibrium should lie to the left. If the conjugate is weak, the equilibrium or reaction should lie to the right. So this is a strong acid. That makes its conjugate weak. So we're talking like one-way arrow, okay? This is a weak acid. That makes its conjugate strong. So it will head back that way, okay? All right. So now we're going to use this with numbers. So the first thing I'd like you to do in both, the reactions are both the same. So let's just, in both reactions, identify the conjugate acid-base pairs. That's the first thing we can do. Identify conjugate acid-base pairs based on these definitions we've learned. They're the same two reactions, so I just relabeled the bottom reaction. So it's just two different questions. It says, based on the information above, which is the strongest acid? Well, that's because there's two acids in there. There's this acid, and there's this acid. An acid and a conjugate acid. They're both acids. So I have to pick who is stronger. Now, the only way to do this, well, there's two ways. One is if you know the identity of these guys. Or, since I don't know who these are. H something. HCl, HBr, HF, HNO3, HClO2, H whatever, okay? The K value. Now, this is last chapter. This is the last topic of the equilibrium value. So K equals what over what? Products over reactants, right? And this was the equilibrium constant, and this reaction is at equilibrium, so I will have an equilibrium constant. Now, I notice that this K value is relatively big or small. 10 to the negative fifth is a kind of a small number, right? So if K is small, it means at equilibrium, who do I have more of? What will give me a small value for K? A big number in the numerator or the big number in the denominator? More reactants at equilibrium. That's what will make K be so small. So to figure out who the better acid is we want whoever it is to be making more of my reactants. So now you have to know what an acid does. An acid loses a hydrogen ion. So who loses the hydrogen ion to make more reactants? The HX or the HY? This guy, right? When it loses the hydrogen ion, think of it like a tug of war. You have to pick which one. The stronger acid will be the one who loses the hydrogen ion. We want to be making products. So when I lose the hydrogen ion, I want to be making these guys. Well, when this guy loses a hydrogen ion, it makes Y minus. Increasing Y minus would decrease K. If this guy was the stronger acid, it would be the one who lost the hydrogen ion. And if it lost the hydrogen ion, it would be making X minus. That would be making more product, which would make K bigger. So HY is the stronger acid. Now, you eliminated 2 off the bat, right? Because Y minus and X minus were bases, so we didn't even consider those. Okay, so now let's try it again. Let's try another practice. So it says, based on the information above, which is the strongest base? So let's circle who our bases are. We've got this guy, and we've got this conjugate base, both bases. So HX and HY are out, because those are both acids, so they're done. Now, to figure out who the stronger base is, we're going to figure out which way the equilibrium lies. And the way we find that out is by looking at the magnitude of K. K equals products divided by reactants. And K is a fairly large number. Well, in order for K to be large, we want to have a lot of products at equilibrium. So we want to be making these guys. Whatever we got to do to get more of these guys will give me a bigger K. So now in terms of a base, you have to know what a base does. What does a base do? It accepts a hydrogen ion. So basically this guy and this guy are fighting for a hydrogen ion. So the stronger base will be the one who wins and gets to have the hydrogen ion. Now, in order to have the hydrogen ion, you want to match where your equilibrium lies. So the thing that's gaining the hydrogen ion better be making one of these things. So that's going to be this guy, right? If Y minus accepts the hydrogen ion, it will make HY. Making HY will give me a big value for K. If X minus would have been the stronger base, it would have been the one who was allowed to accept the hydrogen ion. And if it accepted a hydrogen ion, it would turn into this guy. Well, making more of this guy makes more reactant. That would be represented by a smaller K. Right? So this will be the last thing we do. The first thing I would like you to do is to identify your conjugate acid-base pairs, please. Okay. Now, it says for the following, proton transfer. This just means H plus transfer. They're using the word proton in exchange for the H plus ion. And predict what the value of the equilibrium lies to the left, so whether K is small, which would be to the left, right? Or whether K is large, which would be to the right. When K is big, you have more products. When K is small, you have more reactants. The way you do this is you have to, so on this problem, you're going to want to write this down. You can't do this without K values. There's no way with this one that you would be able to figure this out. It's not like a known strong acid or a known strong base. So the way we're going to figure this out is by using a K chart, a Ka chart specifically. Ka means we're going to look at acids. Now, that means I'm going to focus for right now on the relative strengths of the two acids, okay? I'm going to compare them and try to figure out who is the stronger acid. So if you're in my classroom, there's actually a Ka chart hanging over there on the wall. The left side of the equal sign means the acid. It's equal sign means equilibrium, okay? And then the right side is the conjugate base side, right? And just like that chart over there, my chart in my room, let's see if I can show it to you. Let me see where I am. It's over there hanging up on the wall. My chart in my room has actual numbers associated, but you don't have to necessarily have numbers right now. You just have to know the ranking or the hierarchy. So let me pull up the chart I sent you the link to. Okay. Up at the top here, you should notice these are your strong acids. All 6 of them. Here they are. Okay. The closer you are to the top of that chart, and the same with the chart in my room, all your 6 strong acids are at the top of that chart. The closer you are to there, the stronger of an acid you are, which means the further away you move, down, 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 until we go over here, down, 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 the worse of an acid you are. So if you're a worse acid, you're a better base. okay? Really, really great acids up here, really, really great bases, and horrible acids down here, which means horrible acids, great bases. Great bases, horrible bases. Great acids, horrible acids, okay? My chart is a Ka chart in my room, so it has all acidic values, Ka values. It's ranking them in terms of acidity. So we said we're going to look at our two acids in here, HSO4 minus and HCO3 minus. So you need to find them on the chart. So HSO4 minus is right here. HCO3 minus is down here. So who's the stronger acid based on this chart? The guy that's closer to the top is the stronger acid. In fact, if you were to look on my chart, it has the bigger Ka value. So it's the better acid. Well, what does that mean, a better acid? Well, a better acid will be the one that gets to lose the hydrogen, because that's by definition what acids do. So when we have to pick who's going to lose the hydrogen ion, the stronger acid will be the one who loses the hydrogen ion. Well, we just said this guy is the stronger acid, so it gets to be the one that loses the hydrogen ion. So if it loses the hydrogen ion, who does it turn into? This guy. Is that right? So our equilibrium lies to the right. We'll have more product than we will reactant at equilibrium because this is the better acid, and it will get to be the winner of who gets to lose the hydrogen ion. If this was the better acid, it would lose the hydrogen ion, but it would make this guy, okay? But it's not. So equilibrium, K greater than 1, I'm definitely making more product because this is the better acid. It will get to be the one that loses its hydrogen to turn into this guy. And so my equilibrium lies to the right. So then the question becomes, do I have to look at acids? And that answer is no. You can focus on the relative strength of the bases as well. So let's do that. These guys were my bases, right? Okay, so I'm going to go back to my chart. And I'm going to find carbonate, and I'm going to find sulfate. So sulfate is right here. And carbonate is down here. Who's the better base? The further away you get from the acid, the better of a base you are, because the worse of an acid you are, right? So carbonate is a better base, whereas sulfate would have been a better acid. Carbonate is closer to the bottom. These are great bases. These are horrible bases because they're your strong acids, okay? So base, better base. Well, what do bases do? In exchange for being the better base will get to accept the hydrogen ion. So if this guy is the stronger base, it will be the one that accepts the hydrogen ion better. Well, if it accepts the hydrogen ion better, who does it make? This guy, right? So we're making product. Again, so K greater than 1, equilibrium lies to the right. The answer shouldn't change based on who you focus on, whether you focus on the acids or the bases. It should remain the same, regardless. It shouldn't go one way and then go the opposite way for the same exact reaction. That would make no sense. So again, a better base will be the better hydrogen ion acceptor, which means if we have to pick who's going to accept the hydrogen ion, this guy does because it's more basic. So when it does, it turns into this, and making more product gives me a bigger K. Equilibrium lies to the right.